In the next portion of this session, I'm going to talk about some regression models that have multiple predictors in them at the same time. And I'm going to be working with this part of the regressiondemos.r code file. So I'm going to go through just a few examples with multiple predictors right now because I'm planning to talk a little bit more about what this is actually doing next week. So let's start by thinking about how the fun and cool ratings are associated with the price of the robots. We would expect that robots that participants think are fun would be more expensive. The participants would be willing to pay more for robots that they think are more fun. And sure enough, when we use rating.fun as a predictor in a simple linear regression model with price as the response variable, and we plug the result of that LM function directly into summary because we're not going to use it for anything else, we can see that the slope is positive, that robots that are 1 unit more fun tend to cost $5.25 more, and that association is statistically significant. Similarly, when we use rating.cool as the predictor of price, when participants subjectively evaluate a robot as cooler, they also are willing to pay more for it. So 1 unit of coolness is associated with $8.28 more price, and that association is also statistically significant. Both of these relationships are consistent with what we would expect, that participants would be willing to pay more for robots that they think are more fun, and they'd be willing to pay more for robots that they think are more cool. But the same participants gave ratings of fun, cool, and price. So I could use fun and cool together to predict the price. And here I'm going to do that. I'm using the plus sign. Rating.fun and rating.cool are both predictors in this regression model. And the plus sign separates predictors that I want to include in the same model without allowing them to interact. Price is the response variable. So what this is going to do is it's going to estimate the relationship between how fun the robot's perceived to be in its price at any given level of cool, and the relationship between how cool it's perceived to be in its price at any given level of fun. In other words, it's going to attempt to fit a regression model with 2 slopes, one for fun and one for cool, that would minimize the sum of squared residuals of price if we calculated estimated prices based on those 2 slopes. And here's the model output. And the point that I want to illustrate here is that the slope for fun is weaker than it was in the simple linear regression model. So 1 unit of fun was associated with $5.25 more price on its own. But adjusting for cool, it's associated with $4.41 more price. And 1 unit of cool was associated with $8.28, but adjusting for fun, it's associated with $7.75. A way of thinking what this adjusting for means is that $7.75 is how much extra price we would expect of a robot 1 unit cooler holding its amount of fun constant. So fun robots tend to be cooler in general, but in this case, we're imagining a robot that's 1 unit cooler, but that has the same amount of fun. And that's why the association with price is weaker. Another way of thinking about it is that $7.75 represents the average association between how cool the robot is and its price at every possible value of how fun the robot is. So if we restricted our sample to only those robots that were exactly a 4 on the fun scale from 1 to 7, and we looked at how cool was associated with price, and then we did that again at 4.1 on the fun scale, and we looked at how cool was associated with price, we wouldn't actually be able to do that because we don't have enough robots at each of those points on the fun scale. But if we imagined doing that, and then we averaged together all the slopes that we would get between cool and price, we would get something sort of like this. That's like a heuristic way of thinking about what's going on. This is the association between cool and price, assuming we already know the information about how fun the robot is. In the next example, I want to look at mass and material predicting price. So here's the simple linear regression with mass predicting price. 1 kilogram of mass is associated with $0.29 more price, 29 cents of additional price, and that's not statistically significant. Mass seems to be basically unrelated to price on its own. We already know that material is associated with price. Plastic robots are almost $10 less expensive than metal robots overall, and this represents the actual mean for the metal robots, $107.50, and the actual difference between the means of the metal and plastic robots. When I include mass and material in the regression model together, then I get the slope of material adjusting for mass and the slope of mass adjusting for material. And some strange things happen. The slope of mass now is negative 0.97, and it's statistically significant. This means that adjusting for material, heavier robots tend to be less expensive. If we were to estimate the relationship between mass and price for the metal robots, and also estimate the relationship between mass and price for the plastic robots, and come up with a compromise between those two relationships if they were somehow different, then that compromise would be something like negative 0.97. So even though mass was not strongly associated with price in general, within the groups of metal and plastic robots, it's negatively associated with price. Heavier robots are cheaper. And the slope of material now is negative 12. We already know that the plastic robots on average were $10 less expensive than the metal robots. What this is telling us is that given information about the mass of the robot, the plastic robots are expected to be $12 cheaper than the metal robots. If we were to imagine an equivalent robot that has the same mass, but only differs in whether it's metal or plastic, that's the difference we would expect. At least under the constraint that we have these two linear associations and they're constrained to be straight lines. It's a little bit difficult to think about what this negative 12 actually means. It's even a little bit difficult to think about what this negative 0.97 actually means. But stay tuned, because next week we're going to talk a little bit more about that. One more example. Here I'm going to use the method of transportation the robot is and how fun the robot is perceived to be. So robots with wheels are $5.81 less expensive than robots with legs. And that association is statistically significant. And this represents the actual difference between the means of the robots with legs and the robots with wheels. Those with legs, $105.54 on average. Here's the linear association between how fun the robot is perceived to be and its price. It's 5.25. 1 unit of fun is associated with $5.25 of additional price. And here is the result of including transport and fun ratings in the same regression model as two predictors predicting price. The difference between the wheeled robot and the legged robot is now not statistically significant. And that was a pretty large difference before. It has completely vanished in this regression model that adjusts for how fun the robots are. So, although overall there was an average difference in price between the robots with wheels and the robots with legs, when we are holding fun constant, imagining robots that have the same fun but differ in their wheels and legs, the difference is not statistically significant. We might be tempted to say that one of the reasons that robots with legs were more expensive than robots with wheels is that they were perceived to be more fun. And we'll come back to thinking about that idea later in the semester. But even within the group of robots that have wheels and the group of robots that have legs, our fun rating is still positively associated with the price of the robot. Robots that are more fun are more expensive, even if they have wheels, and robots that are more fun are more expensive, even if they have legs.